Today we're going to look at the lab identity of a liquid or identity of a compound. We are going to start the lab by collecting measurements and data on a known compound, acetone. So for part A, we are going to collect acetone data for trial 1. So initially, we get a 10 milliliter graduated cylinder, like the one shown in the picture, and we take the mass of it when it is clean, dry, and empty. So your first mass is 33.702 grams. Now this is the mass given when I put the 10 milliliter graduated cylinder on the scale and I recorded all the digits. Next, we are going to add 3 milliliters, approximately 3 milliliters of acetone to that graduated cylinder. So in this next empty space, volume of first sample, you are going to use the picture to the right to figure out what the exact milliliters of acetone are in that graduated cylinder. Remember, whenever you are measuring with the device, you want to go one further than the device allows. So in this case, we are using a 10 ml graduated cylinder. The device goes to the 10th place because you can see 2.1, 2.2, 2.3, so on and so forth. So you want to record your volume to the 100th place, so one further. So make sure you are going out 2 decimal places. It's not at exactly 3 mils, but it is close. So take a look yourself and record the volume. Next, we take that 3 mils of acetone in the graduated cylinder and we bring it back to the scale. We then mass it again. So now the second mass we have of 35.990 grams is of the graduated cylinder plus that 3 mils of acetone. Using those two masses, the cylinder by itself when it was clean, dry, and empty, and then the cylinder with the first sample in it, we're going to calculate the mass of the first sample. Remember, when you're calculating, you want to subtract the sample and graduated cylinder and take out just the graduated cylinder. That will give you the mass of the first sample. Now notice you have the mass and you have the volume. So using those two pieces of data, you can calculate the density. Remember, density is mass divided by volume. In this case, the mass is going to be in grams, the volume in milliliters, so your density would be grams per milliliter. When you are calculating, make sure you are taking into account significant figures. Next, we're going to do trial 2. So trial 1 was with 3 mils in the graduated cylinder, and we're going to add to approximately the 6 mil mark. The graduated cylinder, clean, dry, and empty, still mass is the same because we're still using the same graduated cylinder. What changes is the second mass because we now have more acetone in that graduated cylinder, so the mass of the second sample with the graduated cylinder is going to be more than the mass of the first sample. You're going to record the volume of the second sample by using the picture to the right. Notice it's above the 6 mil mark, so make sure you are reading the meniscus and that you are recording your volume in milliliters out to 2 decimal places, one further than the device allows. To calculate the mass of the second sample, you are going to subtract the 2 masses given. Once again, make sure you are taking into account significant figures. Remember, with subtraction, we're looking at decimal places, not sig figs as a whole. Once you have the mass of your second sample, you can calculate the density, just like in trial 1, using the mass divided by the volume. Don't forget your units. Next, you're going to take the data that you have calculated and do some more calculations with it. So the first thing we're going to do is calculate the average experimental density. So you're going to take the density of your first sample that you calculated and the density of your second sample. taking into account sig figs. You're going to add them together and divide them by 2 to get the average. The more trials you do and average them out, the more accurate your data is going to be. We just did 2 trials for this experiment. Next, you're going to calculate your percent error. Now, there are several different ways that this equation is written. I believe in your lab manual it says actual minus experimental divided by actual. The equation I have chosen to write it with measured minus true divided by true. It all means the same thing. Notice there are bars around the subtraction part in the numerator. Those bars are called absolute value bars. And what they mean is if you get a negative number when you do that subtraction, absolute value says that it needs to be positive. You don't need to change the value itself, just change the negative sign to a positive sign. So you are going to take the measured, and the measured is what you did, your average experimental density. You are then going to subtract it from the true density of acetone. The true density is going to be the density that you find in Table 1. Once you do that subtraction, if you get a negative number, make sure to change it to a positive due to those absolute value bars. Then divide it by the true value of acetone from the table once again. And don't forget to multiply by 100 to get it in a percent. Next, we're going to look at the solubility of acetone in water. Now, notice you have Table 1 that has the solubility written. It says that yes, acetone should be soluble in water. But we're going to mix the two together to see for ourselves. So you can see in the picture to the right, that's actually a mixture of acetone and water together. So what you need to write is whether you think it's soluble or insoluble based off of that picture. So remember, soluble is going to be where they had mixed thoroughly and you'd see no separation of the two liquids. Insoluble is going to be a separation. So you would actually see a line where acetone would be on top and water would be on bottom. But notice we don't see that line, meaning that yes, indeed they are soluble. The last piece of data we are going to collect is the experimental boiling point of acetone. So the reason we're collecting this data is because we're really just trying to hone our skills before we try them on the unknown. So when we do the experimental boiling point of acetone, we're going to take a thermometer and we are going to attach a capillary tube to it. And the capillary tube is what you see right here next to the thermometer. You can also see a little bubble at the end of that capillary tube. So that's the open end of the capillary tube, and it is submerged in the acetone. And what's going to happen is, as we get close to the boiling point of acetone, we're going to see a steady stream of bubbles come out of that capillary tube. When that happens, we remove the test tube from the water bath, and once the bubbles stop and the liquid goes in the capillary tube, that's when we record the boiling point. So when I did this in the lab, I got an experimental boiling point of 55.2. Now you can't see the numbers on the thermometer, but they do go by ones. Go from 55 to 56 to 57, etc. So notice when I recorded the boiling point, I went out one further than the device allowed, 1 decimal place. The actual boiling point of acetone I got from Table 1, and that is 56 degrees Celsius. You're going to need to use these two values and calculate percent error, keeping in mind that the experimental boiling point is your measured, and the actual boiling point from the table is the true value. Now we're going to do collect the same set of data with an unknown. And we're going to use the data that we collect, compare it to the values in Table 1, and figure out what our unknown liquid, our unknown compound is. So we're going through the same steps. I took that graduated cylinder that we used for acetone, put it in the oven to get it dried out, and reused the same cylinder. So the mass of the 10 milliliter graduated cylinder is remaining the same as with the acetone example. I then added drops of the unknown sample into the graduated cylinder up to approximately the 3 ml mark. You are going to use your skills looking at the picture to the right to figure out exactly how many mils. Make sure you are going out 2 decimal places. This time I got a lot closer to the 3 mil mark. Might be just a little bit above it, it looks like. Make sure you record that in milliliters. Next, I took that graduated cylinder with the 3 mils in it and weighed it again. This time getting a mass of 35.624 grams. Now we can subtract those two masses to get the mass of the first sample. We can then calculate the density of the first sample since we have the mass and the volume. That's the density that we're going to be using to compare in Table 1 to try to figure out what our unknown is. Remember, the density is not going to match up perfectly with what the data in Table 1. We're just looking for the one it matches up with most closely. Since mistakes are easily made, we're going to do a second trial just to check our work. The volume of the second sample, I'm just going to add more of the unknown up to the 6 mil mark. This time I overshot, went a little bit above the 6 mil mark. The mass of the second sample, taking that 6 mils in the graduated cylinder, was 37.653 grams. I will calculate the mass of just the liquid itself by subtracting those two masses, one of the empty cylinder and one with the cylinder and sample in it. You are then going to calculate the density of the second sample. Now this density should closely match the density that you got with the first sample. You're going to calculate your average experimental density just like we did with the acetone, adding the two densities together and dividing by 2. You're then going to calculate the percent error of density. You probably won't be able to do this percent error part until you figure out what your unknown is. And in order to figure that out, you're going to want to compare your solubilities and your boiling points as well. So save the percent error until you're sure what your unknown is. Next, let's look at the solubility of your unknown in water. So based off of the picture to the right, you need to tell me if your unknown is soluble in water, and if it's soluble, that means you're going to see no separation of liquids. Or tell me if you think it's insoluble based off of the picture. In that case, you would see a separation of the liquids. So you would see a defined line in between the two liquids separating the two. Just look closely and tell me what you see. This will help you greatly in narrowing down your list of unknowns. Next, we get the experimental boiling point of the unknown. And when I did this in lab, I got 66.5 degrees Celsius. Once again, we followed the same process as we did with the acetone, getting a steady stream of bubbles. Once we had a steady stream of bubbles, I removed the test tube from the water bath, and when the bubbles stopped is when I recorded the boiling point. Now this boiling point is not going to match up perfectly with any of your unknowns. Pick the few that are closest to it, and in combination with what you calculated for density and what you saw in the solubilities, you should be able to figure out what your unknown is. You can see now the live action video and the steady stream of bubbles. This is the point at which I removed the test tube from the water bath and recorded the experimental boiling point. Now, the last part is the identity of the unknown itself. So use that table 1 in your lab manual, compare your solubility, whether it was soluble S or insoluble INS, help narrow it down that way. Then compare your densities. What did you get for your average density? And narrow down even further. And then last, use your boiling point. Pick the compound that matches closely with the data collected. It will not match perfectly. This is experimental data. Once you know what your unknown is, you can then calculate your percent error. Make sure you are calculating percent error for both the boiling point and the density. So use the boiling point in the table. Once you figure out what your unknown is as your true, you will take the boiling point from the previous slide. That will be your experimental or your measured value. Do the same thing with density. Let me know if you have any questions.